The SIC stands for Simplified Instructional Computer. What is the size of memory that is supported in Simplified Instructional Computer? We can access only 1 byte at a time. That is called as byte addressable format. Which are the different types of register that are supported in SIC standard model? Hello everyone, it is Dr. Ravikumar YB. Today we shall have the discussion of the first unit of System, Software and Operating System. How does the machine architecture is defined? How does the machine architecture works in systems is a topic of interest today. Here we have a structural simplified instructional computer. That means we have a simplified instructional computer. Also we call it as in short SIC. The SIC stands for Simplified Instructional Computer. We have two variants of Simplified Instructional Computer. The first one is the standard model, also called as SIC model. The second model is an XE model. What is the meaning of XE? An extra version, where X stands for extra equipment or extra expensive type of model. So you will find a difference between a standard model and XE model. What is the difference you are going to find out in standard model and SIC/XE model? That is SIC model and SIC/XE model. The difference you may observe in these two types of architecture of systems are the instruction formats of these two architectures may vary. The size of data items, that is the addressing modes which we are going to use to refer any of the data items present in memory location, may also be different. So in various aspects we will find some improved functionalities in XE version than standard model version, that is a normal SIC version. But in your syllabus you have only SIC, that is Simplified Instructional Computer, that is SIC model. So let me take you into the details of that SIC model. In this, the Simplified Instructional Computer SIC model architecture can be defined in terms of these. The first one can be a memory. What is the meaning of memory? As you all know that if I want to store any data items in my computer, I must have a memory. The memory may also be a simple random access memory, or also I will call it as a primary memory. Then alternatively I have a secondary memory, also called as a hard disk, wherein you will store all the information whenever the power goes off. Or when the power goes down, you will save all the information which is present in random access memory onto the secondary memory. Right? That is the topic of discussion now. That is a memory, the way in which we store the data items in this architecture. How these data items are stored in these memory locations, and how these data items are fetched or accessed from these memory locations using the different types of instruction set supported by this SIC computer are the topics we are going to learn. That means the architecture of any computer can be defined in terms of these criteria. The first criteria is memory criteria. The second one is registers. Third one is data formats supported by that computer and the instruction formats supported by that computer, then addressing modes used in that type of architecture of a computer, then finally instruction sets and input and output. These are the certain set of criteria we are going to consider to define an architecture of a computer. In the standard model of simplified instructional computer, we have these criteria again. If that is the case, what has to be the memory? What is the size of memory that is supported in simplified instructional computer? Let me tell you that the first criteria is memory. The architecture of an SIC computer shall be defined in terms of memory. Let me take you into that. A memory consists of 8-bit bytes. Please remember that I am using 8-bit bytes. 8 bits are called as 1 byte. We have a collection of these 8 bits of information, so I am calling it as 8-bit bytes. Then, the word, I am using this as 1 bit, another bit, 1 bit. How many bits are there? This is called as the first bit, second bit, third, fourth, fifth, sixth, seventh, eighth. So totally 8 bits are there. These 8 bits are together combined to form a byte. This is one individual thing is called as bit. Similarly, if I have one more byte of information, that is 10, 10, 10, 10, I will call this as another byte, second byte. Similarly, I may have one more information, that is 01, 01, 10, 10. This is called as a third byte. So, if I combine all these first byte, second byte and third byte together forms one word. That is, 24 bits are called as one word. Now, this SIC memory architecture supports these formats. That is, all addresses are byte addresses. That means, if I want to access any memory location, I can access 8 bits at a time. I can access 8 bits at a time. This first bit at one time, this second bit at another time, third bit at third time. That means we can access only 1 byte at a time. That is called as byte addressable format. Similarly, words are addressed by the location of their lowest numbered byte. Together, if I combine the first byte, second byte and third byte, I'll get 24 bits as one word. The lowest address, this is called as the lowest address. This is conjuncted to this. This is conjuncted to this. Right? So totally we have 24 bits. The lowest address. This is called as the lowest address or numbered byte. I will consider that as the word. Words are addressed by the lowest numbered byte. Suppose if I have the first byte, second byte, third byte, I will number this entire word based upon the first byte information. Similarly, how can I say that this is the capacity of the memory? If I have 2 raised to the power of 0, that is 1. 2 raised to the power of 1, that is 2. 2 raised to the power of 2, that is 4. 2 raised to the power of 3, 8, 16. So totally, what is the length of that? If I say that 2 raised to the power of 15, I have to multiply this value to 15 times. I'll get the value maximum of to 32,768. Right? In the same manner, that is the capacity of the machine. Capacity of an SIC architecture. If that is the case, let us see to it. Memory. It is byte addressable. Then we have the second type of criteria, that is register. Which are the different types of register that are supported in SIC standard model? The first one is mnemonic A. The register name assigned to it is accumulator. Please don't forget to remember this accumulator. This is indicated by A. The first character of this word accumulator indicates A. So I have the mnemonic A or symbol A to represent an accumulator. Similarly, an index register. An index register is represented by X. There is a slight difference in the mnemonic or the symbol used to represent an index register. Third one, linkage register. The linkage register is represented by L, wherein L indicates the linkage register. Fourth one, program counter. This program counter helps me to determine the address of the next instruction to be fetched or executed in the program. Then status word. This is the fifth register represented by SW. So we have some words assigned to it, that is the numbers assigned to it, where accumulator as a number 0, index register is represented by 1, then linkage register is represented by 2, then program counter is represented by 8, then status word is represented by 9. Then the purpose of these registers are written over here. When I go on explaining the programs for performing some operations, I will use these registers to store some intermediate data, because a variable can hold only one data at a time. That means a memory location can hold only one data at a time. If I want to have more than one data, I must have some intermediate location or registers to store the intermediate values. Now, if I want to replace one of the values stored in a memory location, I have two values here. One of the value is stored in memory and another is in the user data, that is in the register. Now, I have to replace that with the value present in this register. I have to use the registers there to store some intermediate values. So let me clarify you that A stands for accumulator, X stands for index register, L stands for linkage register, PC stands for program counter, SW stands for status word. These are the 5 different types of registers we have in SIC computer architectural model. When you are asked to write about the architecture of an SIC computer, you must define it in terms of memory, you must define it in terms of registers, and so on like this. What is the data format supported by SIC model? Integers are stored as 24-bit binary numbers. As I have already told you, a word, a 24-bit numbers are called as a word. So these integers are represented by 24-bit words. Then 2's complement representation is used to represent the negative numbers. That is, the most significant bit indicates whether the number is a positive or a negative number. If it is negative, the most significant bit will always be 1. If it is a positive, the most significant bit will always be 0. Then the characters are stored using 8-bit ASCII code. An 8-bit ASCII code helps me to represent characters such as A, B, C, D, so on up to Z. Suppose if I want to enter any of those characters, it is not at all possible to represent those characters directly. Instead, I must have the values associated with that character. For example, the character A must be associated with an ASCII value 65, B must be associated with an ASCII value 66, C must be associated with an ASCII value 67, so on and so forth. Like that, we have the ASCII codes to represent the characters. What is the size of that? 8-bit ASCII codes to represent the characters. Then, the floating point hardware is not supported on SIC architecture machine. A floating point number representation, which was discussed earlier, that is the integer part, decimal point, followed by fractional part. This kind of data is not at all supported in SIC model. That is one of the drawbacks of this SIC model. Let me take you into the instruction formats. This is the general format, which is of 24 bits, where the first 8 bits represent the opcode. Opcode. What is the meaning of opcode? I am using the word opcode. Operation code. Whether the operation is add, whether the operation is sub, whether the operation is multiply, whether the operation is division, those operations are specified by opcode. This may be a add, sub, mul, also called as multiply, division, also called div. These opcodes are defined by whom? Optab. So we have a data structure called optab correspondingly to have an opcode. This optab consists of, again, optab is a data structure that contains the operations symbols, operational symbols such as add, addition, subtraction, multiplication, division. All these are stored here. Similarly, the first 8 bits represent that. Then the next 1 bit is of type x. What is the meaning of x? When the value of x equal to 0, we say that it is direct addressing mode. Direct addressing mode. When the value of x equal to 1, we say that it is an indexed addressing mode. Then what is the difference between a direct addressing mode and an indirect addressing mode? Let me tell you that. A direct addressing mode is a type of addressing mode that helps you to directly access the memory location. In case of indexed addressing mode, you will not access the memory location directly. Instead, you will access the memory location through the index of that. Suppose if I say that this is the memory location 10, 20, 30, 40, 50, these are the memory locations. In case of direct addressing mode, we will access the data items directly from here, from these locations. But in case of indexed addressing mode, we will have an index for these locations, that is 0, 1, 2, 3, 4, 5. 4, that's all. Now, if I want to access this data item, I can access this data item through this value, index. So that is called as indexed addressing mode. In case of indexed addressing mode, x will be 1. In case of direct addressing mode, x will be 0. Then this 15-bit represents the address of this memory location. What is the address of this memory location? 2 raised to the power of 15. That is 2 raised to the power of 0 is what? 1. It is present in first location. 2 raised to the power of 1 is equal to what? Second memory location. 2 raised to the power of 2 is what? 4. That is fourth memory location. So totally if I have 2 raised to the power of 15, I will have 32,768 memory locations. I can access the memory locations right from here to the end of this location. This is called as 0th location on RAM. This is called as first location, second location, so on up to A, B, C, D, E, F. If that is the case, which is the next element? Which is the third element? So on up to, I will have 0, 1, 2, 3, so on up to A, B, C, D, E, F. On RAM or main memory, I can get the final value, that is F comma F. So totally this address is represented by 32,768. So I can access the memory locations right from here to here. So that is the address bit. Whether it is a direct addressing mode or an indexed addressing mode, that depends on the bit position we have, X. If X is equal to 1, we say that it is an indexed addressing mode. If X equal to 0, we state that it is a direct addressing mode. This enables the computer to access the memory locations directly when the value of X equal to 0. When the value of X equal to 1, we have the memory locations, and these locations must be accessed only through the indexes. That is right from the first location to the last location. Let me take you into the next type of addressing modes. That is direct and indirect addressing mode. In case of direct addressing mode, we have the value directly, that is the value of X equal to 0. But what is the difference between, another difference between a direct addressing mode and an indirect addressing mode? In case of this, let me tell you that what is that X? X indicates which register? Index register. Suppose if I have another register called A, accumulator load A or LDA 10. What is the meaning of this? LD stands for load. A stands for accumulator. That is, accumulator register is filled with the value 10. LDA. Then, am I using any indexes here? No. I am not at all using that. If that is the case, I am directly referring to the value 10. I am loading the value. Now, if I want to use the indexed addressing mode, I have to enable X equal to 1. That means I have already defined in the previous slide, that is this opcode. Opcode represents add, subtract, multiply, division. What is the value of X? 1. Add as some specific value. Again, this opcode add as some specific value, that is zeros and ones, 0, 0, 0, something like that. Then subtract also has some value, 0, 1, 0, 1, something like that internally. Then the value of X equal to 1. When this bit, 9th bit becomes equal to 1, it addresses the location directly. Otherwise, it addresses the location through the indexes. So, let me take you into the index addressing mode. In case of this indexed addressing mode, 9th bit will be enabled, that is 1. Then the target address equal to address plus X. What is the meaning of that? You just observe that the target address equal to address here. Here the target address equal to address plus X. What is this X? Also called as the index value. Index value. It depends on the index. That means I gave you the information. If I want to access any of the memory locations, I can access only through the index of that. That is A of 0. In case of C programming language, A of 1, A of 2, so on. What is that? A of 0, A of 1, A of 2. That is an index value. That index value is helping me to fetch the data present in that memory location. So that's why I'm using here plus X. Next, let me take one example here. In case of this add alpha example, add is again an opcode. Alpha is again a symbol. Effective address of this alpha is 1000. That is here. Add alpha. What is the meaning of that? The value present in this location 1000 or the value 1000 of alpha, this is of alpha is 1000. That means we have the value stored in it is 1000. The effective address, what is that? We have a RAM like this. This is called as 0th location, first, second, third, so on up to F. Similarly, we have second row, third row, so on up to F. Here I have F comma FF. So totally I have the values from here to here. Then 1000 may appear somewhere here. Location. Now in this location, if I go there, I will get the data. That is called as that. Then A is equal to A plus alpha. What is the meaning of A there? Accumulator. Accumulator contains the data. Which is that data contains it? 10. Earlier I told you that in the previous LDA 10. Accumulator contains the value 10. 10 must be stored in which location? In this location, 1000th location, memory location. So next, in case of indexed addressing mode, I have two formats here. One is LDA and other one is alpha and the third one is X. As I told you that the effective address of a memory location through indexed addressing mode is calculated by using the target address. What is the target address? Target address equal to address plus X. What is that X? Index. If that is the case, let me take up one example, that is alpha is equal to 1000. That is the 1000th address of this location plus X. What is the index of that? What is the index of that? That is represented by some value called 1 or 10 or 100. 1000 plus 100 is what? 1100. Here I am getting the value, that is the 10 which is present in it through the indexing. Here if I say that again there is a memory location like this, 1000 is present somewhere here. This is the address of this. What is the value present in it? 10. If I want to access that, what is the value stored in it? 10. I can access the data items through the indexing. What is the meaning of index here? Let me write down the exact memory location, that is the RAM addresses. Please listen to me carefully now. That is 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. This is called as 0th. This is called as 0th row. First row, second, third, fourth, fifth, sixth, seventh, eighth. Not 10. A, B, C, D, E, F. which is that 0, f, 0, 1, f, 2, f, 3f, 4f, so on up to AF, BF, CF, DF, EF, FF. So we have till FFth location. Which is the location which is having that? Let me consider the alpha is equal to FF. What is that FF indicates? FF is same as 15, right? F, this corresponds to 15. 15 means what? 1, 1, 1, 1. 1, 1, 1, 1. This is 1 byte. Another 1, 1, 1, 1, 1, 1, 1, 1. See here, 2 raised to the power of 0 is 1, 2, 4, 8. If I add up all these values, what is the value I get? 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. Right? This becomes 1F. This becomes again another F. This location becomes another F. This location becomes another F. So if I consider that the range of values that can be addressed is FF, then this is the address. This is the, what is that? Memory location. Exact memory location. What is the index of that? This is the address of this location. That is 1111, 1111. These 4 ones together forms 1F. This another 4 ones together forms another F here. So totally we have 2 Fs here. This corresponds to this location. Of course, this corresponds to FF. I have a value stored in it. Right? How can I access that? How can I access the data present in it? Through the indexing mode, that is plus X. If I say that alpha is the value stored in it, where is the alpha? That is 1000. And I have the value 10 in this location. 1000 plus this index. That gives me the value of that. Right? This is called as indexed addressing mode. Then we have SIC architecture provides the basic type of instructions, that is data transfer instructions, wherein we will use the opcode of type LDA, load instructions, LDA, STA, that is store accumulator. Then arithmetic instructions like add, subtract, multiply, divide, and all those things. Then logical instructions like and, or, not, or certain type of logical instructions. Then branch instructions. Even in high-level languages like C, C++, we have if statements. Based upon the condition specified in the if statement, we will jump to the next statement which is included within the if block. Otherwise, we will go to the else block. That is like that. Branch instructions, that is conditional instructions. JGT, jump if it is greater than, jump if it is lesser than, jump if it is equal to. Then we have unconditional instructions, unconditional jump, that is jump, J, M. Then we have subroutine instructions. What is that? J sub corresponds to jump from one main function to the subroutine. Then R sub, return from a subroutine to the main function. Then machine instructions like start and end. These are the sum of the instructions formats or the types of instruction set that is supported in SIC architecture. If that is the case, we shall have one more important information here. See here, in this case, I gave you the information. What is that? This is called as an initial address. This is called as an offset address. When does the offset address comes into the picture? When we have a relative addressing mode. Relative addressing mode. What is the meaning of relative addressing mode? Suppose my relation is present in Chamundi Hill. I can go, suppose if someone asks me and come to me, where is your relation or a relative, I can say that this is the present location. From here to the offset, the relative is present in Chamundi Hill. So that is why the initial location is this, and then the offset from here to that location gives me the relative address. But what about the indexing? As I told you that the indexing is referred by this. The same address, that is 10, 20, 30, 40, 50. I have locations like this, 60. Now if I want to refer this directly, I cannot refer it directly. Instead, I can use the index of that. Which is that index I am using? X. When x equal to 0, I say that alpha plus x. That is, this is the location, memory location, wherein this is addressed by this 0, this is addressed by 1, addressed by 2, addressed by 3, addressed by 4, addressed by 5, so on like that. So through the indexing we are going to extract that. But the value which I stored right now, that is initial value plus the offset, gives me the relative address. But this kind of relative address is not at all supported in SIC model, that is in the standard model, but it is supported in SIC XE model. I hope you are following that. The difference between the direct addressing mode, indexed addressing mode, and the relative addressing mode. And of course, the SIC model supports only two types of addressing mode. One is the direct addressing mode and the another one is indexed addressing mode. The third, relative addressing mode, is supported in XE model. Let us take up one of the example program of SIC model. LDA 5. That means what? Load the accumulator A with the value 5. Store alpha. The accumulator contains, right? Store alpha, accumulator with the value alpha. That is the memory location. Then LDCH, load characters. Which is that characters I am supposed to load? Z, char Z. Z has some ASCII value. That is the ASCII value of Z. Z is taken and loaded into the load CH. Then store CH. Memory, from memory to CH. Then reserve word. Which is that? Alpha is the value which is present here. From here to here I have reserve word 1. 5. 5 is present here. The forward reference of that is present here. That is, what is that word? 5 is to be stored here. Then CHARZ, this is present here. This refers to this. What is that character I am going to store? Z into this byte. Then memory. This is going to be stored here with RESB. What is that value? 1. So the transfer operations are, data transfer operations are done here with the help of load accumulator, store accumulator, load character, store character, and all those things are different types of instructions we used to load or to transfer the data from one location to another location. Let us take one more example. Looping and indexing operation using SIC programs. Here LDX. I have X here, load X. In that instruction format, addressing mode, I told you that opcode, first 8-bit corresponds to the opcode, then X. 9th bit, if it is equal to 0, it is direct addressing. If it is equal to 1, it is indexed addressing. Now I have X, which is 0. 0 means what? Direct addressing. See here. str1, X, right? Now, load ch, character x is to be loaded into this, right? str2 comma x, stch, then count tix, jump if less than 0, move ch, then byte. Do I have any value here, that is move ch? Where is that move ch? It is present here. Move characters. Similarly, I have str1 here, str2 here, count here, and 0 here. Where is this str is present? This is referenced here. str2 is referenced here. Count is referenced here. So we have the referencing variable in the future. Future reference. That means I'm using the variable str1 and loading it to the characters. Loading the character. Which is that character? The character x is being loaded into this LDCH. This is an indexing operations. Then we have str2 which is referenced in the future. Now I have the character x. It has to be stored in the character stch. Then we have the count of that. Where is the count present? Count present is here. What is that word present in it? The value 4. Now with this, I will say that count is present here. Move ch. When it comes to move ch, it jumps from here to here once again. Again, stx, str1 comma x, it refers to this. Once when this becomes condition JLT, that is jump if less than, becomes wrong, or when the condition fails, it moves from here to the next subsequent statements. It is similar to if condition. If x is less than 0 or 10, do this set of operation. These set of statements are executed within a loop. Once when this condition fails, it comes out of this for loop and executes the set of statements which proceeds ahead. The same thing is done here. This is through the looping and indexing operations with SIC model. Thank you very much. Thank you all.